Hi, and welcome to 10.2 Transfer of Charge. In the last video, we talked about charge, and I drew a couple examples where electrons were going from one object to another. It either became negatively charged by gaining electrons, or it became positively charged by losing electrons, right? So if you lose an electron, you have an excess of protons, giving you a positive charge. So we're going to talk about three different ways that you could transfer charge. There's charging by friction, charging by contact, and charging by induction. So let's talk about those real quickly, and then we'll handle these problems. So if you charge something up by friction, it's because you're rubbing something against another object. So you might have experienced this with the plastic slide. So you rub down, you go down the slide. Lots of fun here. You go down the slide. And as you go along the slide, your butt is rubbing against that plastic slide. So by rubbing, you're ripping electrons from one object to another. So it all depends. How do you know which object gains electrons? And by using something called the Triboelectric Series, you could determine where the electrons are going. Are the electrons being ripped from the plastic slide to your cotton clothes, or are they being ripped from the cotton clothes to the plastic slide? So the way you use this is it's a list of materials, and the higher up it is, in this case, the more likely they are to lose electrons and become positive. So leather and rabbit fur, they don't really care about their electrons. They'll give electrons away, no problem. They'll go anywhere below them here. And we have, on the other side of the list, they're more likely to gain electrons and become negative. They're like electron thirsty. They'll suck up any electrons as long as it's given to them from something higher up on the series. So let's look at it here. We have a plastic slide, right? So you look for plastic. Plastic's right here. And let's say we have cotton clothes on, and you have cotton right there. Or even, you might have noticed this maybe with your clothes. Maybe you notice your clothes are kind of clinging to the slide, but maybe with like the hair on your arm even. So human hair is even more higher up or further away from plastic here. So where are the electrons going? Are they going from the human into the plastic, or are they going from the plastic into the human? Well, you use your series, and the human hair is more likely to lose electrons and become positive. So, yep, the electrons are going into the plastic. So now this slide, as you go down, the slide becomes negatively charged. And where does it get that negative charge from? It comes from you. So your electrons left you. So not all of them, but some electrons left you. And now you're left with a positive charge. Because if you think about an atom, it has a nucleus made of protons and neutrons, and it has electrons orbiting it. So let's say it's a neutral atom, and the electrons are all circling it. All right. And let's say you lose an electron, just like we did with our slide here. An electron leaves you, so that means that you're losing an electron here. Now you only have this many. Even if you just lose one, what is your net charge now? Well, you have 4 positive things and only 3 negative things. So you have more positive things than negative things. So by losing an electron, you become net positive. You have more protons than electrons. So you left with a positive charge. So this is all positive. And that's why your hair is attracted to the slide. When you go down, you might have felt the hair tugging on your arms, or even with your head if you have long hair, or your clothes even. That's why it's tugging on it. Why is it tugging on it? Because you have a positive charge here and a negative charge with the slide, and they're opposite, and opposites attract, right? So the positive is attracted to the negative is attracted to the positive, and you feel that force. So that's how friction works. You're left with a positive object and a negative object. So that's kind of like the rule. Friction, 1 positive, 1 negative. All right, let's talk about the other way to charge something. So now we're charging by contact. If you charge something by, you're left with either both positive or they're both going to be negative. So when I talk about both, I mean like, okay, one object for friction it was a human and the other object was a slide. It could be a piece of rabbit fur and a piece of PVC pipe, plastic pipe, but you need two objects, right? So for friction, they had opposite charges. For contact, they're going to have the same charge, and I'll show you how that happens. Let's say you have a metal sphere on an insulating stand. So it's like a plastic stand in a metal sphere, and you have another one. Or no, let's say we have like a rod of some sort over here. All right. And let's say that the metal sphere is initially neutral. So yeah, it has sense, but it also has an equal number of electrons. So we say it's a neutral object. Okay, so now let's say we have a negatively charged rod that's being brought near it. Sure, again, you could have some protons here. But since it's negatively charged, not only do you have enough electrons to balance out those protons, but you have an additional excess of charge here. Let me draw one more. Okay, so now this is super negative. This object here, the rod, is very negative. All those electrons, they're repelling against each other because they're all negatively charged and they want to get away from each other. They're repelling against each other. As soon as you bring this into contact with the metal sphere, you're giving the electrons somewhere to go, and they're going to try to form an equilibrium where both objects have equal amounts of charge. So again, this thing is packed with electrons. They're repelling against each other. Finally, they have room to go. They're going to transfer over to the sphere so that they all balance out. They're repelling against each other equally. So I drew 1, 2, 3, 4 excess electrons on purpose because now it's going to balance out and become an equilibrium. Two of those electrons are going to transfer over, and now an equilibrium has formed. So let's see what happened. We still have, so there's one neutral atom, 2, 3. We still have 1, 2 excess electrons. This negative rod is still negative. It's not negative as it was before. Like there was 4 bouncing around in there. Now there's only 2. So now we have a negative rod. And let's see what happened to the sphere. The sphere gained 2 electrons. There's 4 neutral atoms, and again, 2 negative electrons. So an equilibrium has occurred. The sphere was given a negative charge, and we could separate them now. And as you can see, both objects are left with a negative charge. I'll try to quickly go over how you could get both positive now. Let's say instead you start with a positive rod. So now there are 2 neutral atoms in here being shown, and you have an excess of 2 protons. So the rod starts out positive. It's thirsty for electrons. It needs more electrons in order to become neutral. So what we could do is we could bring it close and make contact with that metal sphere. So now it could rip some of the electrons away from the metal sphere in order to try to make an equilibrium. So the metal sphere lost an electron. One of these electrons were brought over here, and because it lost an electron, now it has an excess electron, and the sphere is positive. If you count them up, we have 3 neutral atoms, 1 excess proton now, so the sphere is definitely positive. And we have 1, 2, 3 neutral atoms, but we still have an excess proton. So the rod is positive. Now again, it's not as positive as it was before, but it's still positive. And the metal sphere started out neutral, and now that's positive as well. So they both became positive. So either way, you're either charging with a negatively charged object, or in this case, it was a positively charged object. And if you're charging by contact, they're either both positive or both negative. They have the same charge. So this was same charge. And if you charge it by friction, it would be opposite charge, because an electron is going from one to the other, and then it's being attracted. let me draw it for friction here. With friction, you started with two neutral objects, and the electron left one object, leaving it positive, and it went into another object, making it negative. So since they were both neutral at first, then you have this charge difference. With charging by contact, one object is always charged up, giving the other object the same charge. Okay, here's the third type. It's called charging by induction. Charging by induction is kind of similar to contact. We'll start it the same way, but you don't actually have to make contact in order to charge the object, in order to give it a lasting charge. So let's start with the same metal sphere. Okay, so we have a neutral metal sphere, and let's go with a negatively charged rod. Now, my goal is going to be to use this negative rod. It's got so many excess electrons. How am I going to use this negative rod to give this a positive charge? How can that be possible? So it's almost like friction, where one object is going to be left with a positive charge and one object is going to be left with a negative charge. Basically, you'll be left with two oppositely charged objects. But I'm going to do that by not even touching it with this charged object. Instead, I'm going to ground it. So this metal sphere is still neutral right now as we have it drawn. And let us bring this this rod close. Let's bring it close, but we're not going to touch it. All right. So now we're inducing a charge on the electroscope. What's happening is this negatively charged rod here is repelling away all of the electrons on this side of the object. They're going over here. So since this is a metal sphere, the electrons are free to move about the object, and they're all trying to get away. Look, they're all crowded. It's like this guy stinks, and the electrons are like, oh, get away from me. You really kind of smell. We're not attracted to you. We're repulsed by you. We're repelled. The electrons are trying to get away. So what we did was we kind of polarized this metal sphere. You're left with a positive pole, and you're left with a negatively charged pole. That's all polarizing means, is you're left with one side that has one charge and one side has the opposite charge. Okay, so we polarize the object, but we don't have to draw all this mess inside of here. We're just showing where the electrons went. So the electrons are trying to get away from there. I felt bad for those electrons. Let's give them somewhere to go. By grounding the object, we're literally putting a line, like an electrical line, attached to the object, and this is the symbol for ground. And the electrons are now free to move. They go through the wire. They're like, yes, we can finally get even further away from this smelly thing, and we can leave the object. And yes, okay, enough of us have left. That's pretty good. It's okay if you still have a couple excess electrons here, but electrons have left. That's the point. Or you could draw another one. Why not? An electron is left. They're in the ground. They're happy now. Oh no, I took a proton out. Never do that. It's only the electrons that move. The protons never move. Okay, the protons stay right there. Okay, so now the rod was brought close. You polarized it. You connected ground. Electrons left. And now what you do is you take away the electron's mode of transportation. Boom. You cannot get to that sphere anymore. The electrons are stuck in the ground. All right, they have no way to get back into the object. And when we move this rod far away now, let's see, the rod didn't change its charge at all. But now, since the electrons left the charged sphere, or the neutral sphere, now it's left with a charge of a positive charge, all right, because there's more protons than electrons now. And we did what we predicted. We were able to give this thing a positive charge with a negatively charged object. And that's what charging by induction is. I'll show it really quick with positive. So now let's say we have a positively charged rod, and we bring that guy near the electroscope. All right, but we're not touching it. All right, that's the whole point of induction. You bring it close, but you don't touch it. Now, if we bring this positively charged rod here, all those electrons, they are not repulsed by that guy. They're like, whoa, that's a positive object. I am attracted to that. Let me go over there. Boom. Wow, look at that guy. It's like a crowd of people coming to see a celebrity. They all want to get close to it. And look what happened. We are polarizing the object again. We have a positive pole where the electrons left that, and we have a negative pole. They're all crowded on this side. So we have a positive side and a negative side. All right, again, we'll get rid of this mess. We get the idea. That's where the electrons are going. Now, all of a sudden, let's open the floodgates. So, yeah, it's like a celebrity's here in a restaurant, and all the people are crowding around the poor celebrity, and all of a sudden the door opens, and the paparazzi come in. You connect this thing to ground, and the ground has plenty of free electrons to give up. That's the whole point. It's like the ground is literally planet Earth, and it could either readily give electrons, and the whole point is it's trying to form an equilibrium, right? So it has so many electrons that it doesn't mind giving up some electrons in order to make this positively charged object not as positive before. Or in the previous case, we gave electrons to the Earth because there were so many electrons packed in this thing, they went down into the Earth. Because the Earth is like, whatever, you have a negatively charged object up there. I'm trying to make an equilibrium with you. No skin off my nose. You could put a couple electrons in me and it's not going to matter as compared to this object here. So now all these people are flooding into the restaurant and they're trying to get near this guy here. Yeah, we could even draw it like this, right? So they're all still attracted to him. And now all of a sudden, don't want to move the proton. Can't move that proton. It's only the electrons that's moving. So move the electron. All right. Now the whole place is crowded. The restaurant's crowded with all these people that want to get near the celebrity. But the celebrity is free to move, and they move away. Luckily for the celebrity, they got a backdoor entrance and exit that they could go to. Oh, man. And now this isn't polarized anymore. We could spread out the charge equally throughout the sphere, because all the people are now trying to they're like, oh man, I don't want to be near all these random strangers. I wanted to be near that celebrity, but they're trying to so the electrons repel against each other and spread out pretty evenly among the object. And now let's see what we're left with here. I have, let's circle them. We have some neutral atoms, but we have an excess of 3 electrons. So this thing was given a negative charge by a positive object. It's important to note that no touching, except if you count the grounding as the touching. All right, but the charged object doesn't touch the neutral object. And you're left with opposite charges. All right, so you need to understand these concepts in order to understand. I'm going to go through these problems. The problems are kind of just refer back to these rules. So I'll write these rules on the top of the page so we can reference them. And if you get lost again, you might have to rewatch my explanation of these. I'm going to try not to explain it again every single time because it's already 18 minutes in. Okay, number 1, when a neutral metal sphere is charged by contact with a negatively charged glass rod, the sphere becomes what? So we're charging it by contact. It's a neutral metal sphere being charged with a negative. So for contact, it's going to be the same. So it's going to be negative. When a neutral metal sphere is charged by induction, so it's induction and it's a negatively charged glass rod, it's going to be opposite, so positive. Use the diagram to the right to show which shows the Triboelectric Series to answer the following question. When a piece of styrofoam, where's styrofoam? Right here, is rubbed with a piece of silk, which is right here, the styrofoam becomes, well, this is becoming more negative, right? It's closer to that side of the series, so the styrofoam becomes negative. When a neutral metal sphere is charged by contact, so we're talking about contact, with a positively charged glass rod, the sphere becomes positive. So first of all, let's say it's the same. It's a positive by contact, so we're looking for something that tells you it's positive. Now, before we said that we don't transfer protons, and I explained that a little bit in 10.1. we're never moving protons around. We're only moving electrons. So if you gain electrons, this would make you negative because the electrons are negative. But if you lose electrons, that leaves you with an excess of protons. So you become positive. And that's the answer we're looking for, right? Because you're charging by contact with a positive rod. So we're looking for something that makes you positive. Number 5, when a neutral metal sphere is charged by induction with a positively charged glass rod, since it's induction, it's opposite of positive, which is negative. And again, we're not gaining or losing protons, and gaining electrons makes you negative. Use the diagram to the right, which shows the triboelectric series. When a piece of glass, where is glass? Right here. When a piece, okay, get rid of these guys, is rubbed with a piece of paper, the glass does what? So the glass is higher up. It's going to become positive. So the glass becomes positive. So we want it to lose electrons because that's going to give you a positive charge. Number 7, an electroscope is a device with a metal knob here, a metal stem, and freely hanging metal leaves. So these could rotate around, get really close together. And yep, that's what the electroscope looks like. And it's used to detect charges. So it's a scope. It's an electroscope. It detects charge. The diagram below shows a positively charged leaf electroscope. You have 3 different rods: positively charged glass rod, a negatively charged PVC rod, and a neutral wooden rod. You bring each rod close to the electroscope, but do not touch it. Which rod will make the leaves separate more, or bring the leaves close together, or have no effect? So here are your rods. You have glass, PVC, which is just plastic, and wood. You might have seen PVC before with like some plumbing, the plastic plumbing pipes, or in a classroom. So let's see what happens when we bring a glass rod close to the knob. Did I say glass? Glass. Positively charged glass rod. So now we're bringing it like to the top over here. The positive charge is going to attract electrons. And even though this is showing just positive charges here, it's important to note that, let's see, you got this, right? It's important to note that there are still some electrons roaming around down in those leaves. It's just that when you find the net charge, you have an excess proton. So there are still electrons here. It's just that you have an excess of positive charge. And that's true all around. So you have 1, 2, 3, 4, but it's positively charged. So you have maybe 1, 2, right? So you still have a net positive charge that aren't being balanced out by the electrons. So what's going to happen if you bring this positive glass rod near it? Well, these electrons down in the leaves get attracted to that positive rod, and some of the electrons go up to meet it, and this becomes even more positive than it was before, so it's going to separate more. So the glass definitely makes it separate more. Let's see what happens if we bring the PVC rod close. So now you're bringing this PVC rod all the way over here, and oops. Well, now what's going to happen? It's a negative rod, so what are the electrons going to do? All right, the electrons are the thing that's moving, right? So are the electrons attracted to the PVC rod, or are they repelled? They're going to be repelled, so the electrons go down into the leaves, and what you'll notice is that the top becomes more positive, right? But the bottom kind of neutralizes out. They might still be kind of separate, but here you can see that's all neutral atoms down here. So they're not going to be as repelled as they were before. So the leaves get closer together when the PVC comes close to it. Let's see what happens when the wood's brought near. Okay, so you bring the wood close, and oops. You bring the wood close, and it's neutral, so it has no effect. It's easy to say that. All right, no effect on the wood. So let's just leave it at that for now. If you have any other theories of what the wood might do, it's neutral, then leave it in the comments below. Make sure you hit that like button, I guess. Okay, number 8. Which diagram shows an induced charge separation when a positively charged object is held near an electroscope? So we need a positively charged object to test this out. Okay, this positively charged object is going to attract any electrons that are left in the things, making the top negatively charged. So A, the top is positively charged. That's not looking too good. B, this is showing that the negative electrons are repelled into the leaves, but the negatives should be attracted to this positive thing. The opposites attract, so that's no good. And you bring it over here, it's showing the top and the bottom are still neutral, and that's not what would happen. We want the electrons to leave the leaves and go into the top, and that's what's happening here. All right, so any electrons that are left over here, they get sucked up to the top because they're attracted to this positive rod. So the top is negative, and since they left the leaves, it's leaving the leaves with a positive charge. The protons are still down there. Now there's more protons than electrons because the electrons are all on top. And this is how you polarize an object. You induce a charge separation. So it's separated into positive and negative poles. Number 9. A negatively charged object was used to give an electroscope a positive charge. Okay, so now we have a negative and a positive. The electroscope was charged by contact. Nope, that's supposed to be the same. Conduction is another word for contact. It's the same. Induction is looking good. Reduction is some kind of chemistry stuff that we're not talking about right now. So induction is the opposite, which is what we're looking for. I was worried they say friction in there too, right? Because friction is the same end result. You're left with opposite charges, but it doesn't. It says reduction because that's ridiculous. Number 10. 2 identically sized metal spheres, A and B, are on insulating stands as shown in the diagram below. Sphere A has a deficiency of 1.2 times 10 to the 9 electrons. This means it's deficient in electrons, so it has this many excess protons. So it's deficient that many electrons. It needs this many electrons in order to become neutral, right? So that means that there's an excess of positive protons right now. All right, let me draw a little diagram to show. Okay, so here you have a metal object, and I'm drawing neutral atoms here, and there's one that doesn't have an electron. It just has a proton, right? So would you say there's a surplus of electrons, or is it deficient in electrons? And how many electrons are we talking about here? So I would say this is missing exactly 1 electron. It's deficient in 1 electron. So we're taking away 1 electron. It's deficient in 1 electron. So how many excess protons does it have? Well, these 3 guys are happy to be just neutral, but there's an excess of 1 proton. So it's the same magnitude, right? So if it says it's deficient 1.2 times 10 to the 9 electrons, that means it has an excess of 1.2 times 10 to the 9 protons. All right, but this is, I wouldn't even really say positive. It's just the number, the number of electrons, right? So N is equal to that. And B is neutral. Okay, so this is positive. Boom, we understand that now. This guy is neutral. Which diagram shows the charge distribution of sphere B? Interesting. So I drew this wrong here, right? Because initially it's neutral, and then you bring them kind of close, and you can induce a charge separation. And what's going to happen is, since the A is positive, any electrons that are in B are going to be attracted to A, right? Opposites attract. So all the electrons are crowding around this side of B. Sometimes it helps, instead of drawing the positive and the negative signs, you could draw in like little circles if you want to represent the atoms. So here we have our neutral sphere, and you bring a positively charged thing close to it. So these electrons are going to be attracted to one side of the sphere. So the electrons are free to move. It's a conductor. And the electrons are like, oh, wow, look at that positive thing over there. I'm very attracted to that. All right. And what you're left with is a polarized object again. One side is left with a positive charge, and one side is left with a negative charge, and that's what we're looking for in these objects. So this one's all positive. This one is looking good. This one's all negative. This is the opposite of what we want, because the positive charges wouldn't attract a positive side on this side. The electrons wouldn't be repelled by this positive thing. They would be attracted to it, so that's no good. We're looking for B. Very good. Number 11 says a negatively charged rod A is used to charge rod B by induction. All right, so, okay, and then an object C. Better draw a picture here. So negatively charged A is charging object B by induction, so that means it's left with opposite charges. So this is A, this is B. Induction means it's opposite. Object C is then charged by direct contact with rod B. All right, so now we're charging it by contact, which leaves the objects with the same charge. The charge on object C is positive. And again, look back at my explanation of what charging by induction and charging by contact is, if you're confused by that. That explanation was in the beginning of the video there. Okay, so number 12, this one's a good one. It says, what is the smallest electric charge that can be put on an object? So let's say you want to charge this object here. Let's say you're charging it, I don't know, charging it by contact with a negatively charged object. Okay, what is the smallest amount of charge you could give this thing? So let's think about it. If this is initially, it's a neutral object, the smallest amount of charge I could give this thing is just one extra electron, or maybe I take one electron away. All right, so let's talk about the electron going from here into here. It's only one of them. One. You can't have half of an electron. You can't have 0.5 electron. You can't have even 0.9 electron. You could only have one electron. That's the smallest amount of charge that you could move from one object to another. So the answer is the charge for that one electron. It would be 1.6 times 10 to the negative 19 coulombs, either positive or negative, right? If you lose the electron instead, so now the electron is being ripped from here and it's going in this direction. All right, we're giving this a positive charge. All right, there's an excess proton now, but you can't have half of a proton, let's say. So this is the smallest amount of charge you could possibly have. That's going to help us with 13 and 14. If you didn't get 12, it'd be hard to do 13 and 14. It says a particle could have a charge of what? Well, the smallest charge is 1.6 times 10 to the negative 19. So it's impossible for it to be 0.8. Can't be half of it. Can't be 1.2. 3.2 or 4.1. Let's see. What we got to do is we do 3.2 times 10 to the negative 19 coulombs, and you divide it by 1.6 times 10 to the negative 19 coulombs. You're basically doing Q is equal to NE. All right, so let's do that instead. Basically, you should get to a whole number when you do that division. So if you want to just do that, if you get to a whole number, you're good. Double check number 4. Let's talk about Q is equal to NE. The total charge here that's showing 3.2 times 10 to the negative 19 coulombs. We're looking for the number of electrons or number of protons, and it has to be a whole number. It can't be a decimal number because it has to be either 1, 2, or 3 electrons, and the charge for each electron is 1.6 times 10 to the negative 19 coulombs. So you do the division. It's the division that I just showed, and you get exactly 2 electrons or 2 protons. In this case, since they said a positive charge technically, so let's say 2 protons. That is good. We want a whole number. If you do the same thing, but instead type in 4.1, you get a decimal. It's like 2.56. You can't have 0.56 protons. Are you crazy? You want to split up that proton? That's not a valid amount of charge. All right, so let's see. We want to do the same process here. It says an object cannot have a charge of what? So we're looking for the decimal number because That's impossible. It cannot have that charge if it's a decimal. So let's do 4.8 divided by 1.6, and you get, all right, so then you get exactly 3 protons, so that's good. And if you do 6.2, you get an answer. So 6.2 divided by 1.6, you get this weird answer of like 3.875. So that's no good. You can't have 0.875. All right. It needs to be a whole number. That's not good. That's looking like that's our answer because you can't have it. And if you did 8.0 divided by 1.6, you get an answer of 5, exactly 5 protons. So that's nice. And if you do 9.6 divided by 1.6, you get an answer of exactly 6 protons. So again, 6 whole protons, that's fine. All right, so there you go. Have a good day.